Hello, good to see you again. It's lecture 8 time. So, lecture 8 of the series on tectonics and geodynamics. We'll just continue from where we left off. So, we will continue to talk about how plate boundary movements take place on a flat earth. So, we will continue with what we were doing in the last class, and we will carry on from this particular part. So, the concepts that we will try to address here is how to analyze three plate systems and their boundaries on a flat earth. So what would be the types of geometry that would form, right, as movement continues over time. So let's just now go back first to the first thing we were talking about. The first type of three boundary systems we were actually discussing were cases where the boundaries were orthogonal and non-collinear. So the sort of system we had, just to refresh your memory once again, we go back to the black slides, the black color, right? So once again, with apologies for my drawing. So this was the sort of system we thought of initially. So we had a system here and right. So I hope my drawing would give you hope, because this is the kind of drawing which I do extremely poorly, right? So we talked about B, this is A, and this is C. So if you remember broadly, right, so you had this a mid-oceanic ridge at this on the western part of plate B, which was along which plate B was being separated from plate B at a half spreading rate of 2 centimeters per year, which means that the relative velocity of B with respect to A or A with respect to B was actually 4 centimeters per year. As a consequence, this particular segment of the boundary, which is now oriented differently, so this would now become a transform fault, right, with which would be sinistral in nature, right? It would have a velocity of 4 centimeters per year, right, moving along here. The boundary between A and C, right, we can actually just go about it the other way and say that this is what is given to us. So this is at the rate of 3 centimeters per year. And the question that we could answer was, what is the nature of this particular boundary? And as we saw, when we apply, right, say in this case now, if we try to find out the boundary between plates C and B, the relative velocity between boundaries C and B. So the way we write it is, once again, just remember, so the stationary plate here, the way you write it is the B would come first here, and this would be A. So first of all, we say that we represent this as a sum of the relative velocity vectors of A with respect to B, plus, then we just reverse the order. B, A now becomes the fixed plate, and C becomes the one that we want to find out. So the relative velocity of C with respect to B, ultimately, you can think of the two V's, C being on the right hand side of this V here, B being on the left hand side of this first V here. And if you try to remember to write it in this form, so you'll actually never go wrong. Now, as we saw, the relative velocity vector that we had told us that it was a vector like this, right, which meant that the boundary between B and C had to be convergent, but this convergent boundary had to have an element. It had to have an element, right, of strike slip faulting. So it would be in that sense that you'd have a component this way and a component this way. So you'd have a component of dextral strike slip movement actually associated with this. So nevertheless, this boundary is predominantly a convergent boundary, because there is a significant component of the velocities which are acting towards the boundary itself, which means that there must be convergence. Now, the information that has to be given to you is even if it is a convergent boundary, you can tell from the vector triangles that it's a convergent boundary. What you cannot tell is how the system would evolve with time. For that, the extra information that has to be given is which one is the subducting plate and which one is the overriding plate. Now, that is a very essential part of the whole thing. So we have to give you that information. So we can look upon it in two ways. We can think of B subducting below C, in which case the triangles would be pointing like this. So if B is subducting below C, right? So this would be one particular case where B subducts below C. When B subducts below C, right, you would get you'd get a situation where this plate B, right, if the convergence rate is such that it would actually exceed the rate at which it is being produced, then B will grow smaller. Otherwise, B would simply expand with time also. So this particular boundary itself, right, would be a combination. It's what we would call a transpressional boundary, in which there would be a component of convergence, compression, combined with strike slip movement or transform movement. So it's a transpressional boundary. So in this case, right, this would be the case. However, the whole thing would be quite different if you looked at it in a slightly different way. So if you take the same system, right, we draw it the same way, right, exactly the same way, except that now we change we have this, we have this, we have this. Now let's say the overriding plate is plate B, right? So this is plate B, this is plate A, this is plate C. Now in this kind of situation, right, so you can take the same values here. So this would be 4, this would be 3, right? And this would be my convergence vector as it was here. So this convergence vector, now the situation is slightly different. Now B is the overriding plate. Now if B is the overriding plate, how would this geometry actually evolve with time? Now this is a question that you cannot answer just by solution of the relative velocity triangles. The relative velocity triangles actually can tell us exactly about how the motions would evolve, but they don't actually give us the information. They do not actually give us the information as to how the geometry of this particular configuration would change with time. So that is an extra bit that we need to look at, exactly what would happen. So to understand this now, we have to understand exactly how the geometry changes with time, and that is another aspect that we look into, looking at another combination of systems. Now in both of these cases, the case that I showed you before, where C was the overriding plate and B was the subducting plate, right? The geometry of this particular, of this part would evolve differently from the geometry in this case. So these two cases are distinct. So as you can see, the polarity of the subduction exerts a significant control as to how the system would evolve with time. So this is something that we will try to look at now. Now, to look at this, now we've talked about orthogonal boundaries. So these are all either orthogonal and they are also orthogonal. They are also non-collinear. So this boundary is not collinear with this. But suppose we had a system which was a little different. So the system, let's make it apparently simpler. So let's again think of a system where you have orthogonal boundaries and collinear boundaries. So if you have again a 3-plate system, right? So let's call this plate C, let's call this plate A, and let's call this plate B. Now let's say we have a 3-plate system, plates A, B and C. The boundaries between A and B is orthogonal to the boundary between A and C, but the A and C boundary is also collinear. It's on the same line as the BC boundary. So the BC boundary and the AC boundary are represented by the same straight line. So you've got the same straight line passing through, which combines the boundary between A and C as well as B and C. So it's an extension of the other. Now let's also make this a little different now. Let's just think of the relative velocity vectors. Let's say the boundary between A and B, so the AB boundary, let us say it's convergent. Okay, so we'll treat it as a convergent boundary. So, and let us say that it is, the direction of movement is exactly at right angles. Let us also, in this case, provide you, and this is an information that has to be given, I have to indicate which is the subducting plate and which is the overriding plate. So let's put it this way. So in this case now, we've depicted the system in such a way that the polarity is such that A is the subducting plate and B is the overriding plate. So A is the subducting plate, B is the overriding plate. Let us say that this relative velocity, right, the relative velocity of, say, oops, sorry about this. So we'll just get back to this. So the relative velocity of say B with respect to A, right? This relative velocity, let us say this is equal to 4 centimeters per year. So just find it nicer to write it this way. So you can just think of this being the system between the two. The other hand, let's just think of a system where you have the boundary between A and C being a dextral transform fault. And let's say that this dextral transform fault, right, this is, the length is 2 centimeters per year. So these two have to be of the same length. So this is not to scale. So, okay, just to make it a little larger. So 4 is larger than 2. So you can think of it this way. So we now have a 3-plate system. The 3-plate system in which the boundary between A and B is a subduction zone. A subducts below B. B is the overriding plate. A is the subducting plate. Now the boundary between A and C is given as a dextral transform fault. So the relative velocity vector between A and C is parallel to the boundary between A and C. That is why it's a transform boundary. And let us say that the relative velocity between C and A, the relative velocity between C and A, this is equal to 2 centimeters per year. Okay. So now the question that we would like to ask, let's just make it red now. So for the question now is this boundary. We would like to know what is the type of velocity that we have between, what is the relative velocity, let us say, of C with respect to B. What is this? Now we know, just keep this in mind, that the relative velocity of C with respect to B, right, is also equal to, whatever it is equal to, would also be equal to minus of the relative velocity of B with respect to C. This means that the magnitudes are identical, but whatever is the relative velocity, right, it would be just the opposite on plate B with respect to C, opposite to what it is for C with respect to B. So we need to understand what this is. So this is the problem that we're faced with. So that is question number 1 that we can frame in this context. What is the nature of the AC boundary, right? We would like to know what the nature of the AC boundary is. So this is something that is important for us to understand. However, there is a second thing that we can think of. Imagine yourself to be an observer. Let's say you are an observer situated at that particular point. Okay, so let's say you are an observer here. Now the observer who is located here is looking across the plate boundary. Now what is he seeing? So the person who is here is at the boundary close to C and A. So when he looks over this particular boundary, he can't see the boundary, he can see that there is something different happening along here. So according to them, right, if the person lived long enough, would actually see another person who was on plate A would actually be moving northwards at the rate of 2 centimeters per year. Because if this person is an observer here, so essentially this person can be imagined to be fixed. So in that case, plate C is, this person is fixed on plate C. Plate A is moving with respect to plate C. How is it moving? It's moving at the rate of 2 centimeters per year. So this is known. Now, one of the things that is important is for us to understand how this whole system, right, how this whole system will change with time. Will it actually change with time? Will there be a difference? In that case, the important question for us to understand is not just the relative velocity of C with respect to B or B with respect to C. It's not just that, it is also the relative velocity of the AB boundary. How does the boundary between plates A and B appear to move to an observer who is on plate C? Now that's actually a very vital part thing. So we need to understand exactly how this boundary would actually change. How would this actually move? So let's actually get about trying to answer this question. So how do we set about it? So once again, let's just draw this in. So I'll just repeat the drawing here. So we have this particular system. So the system is plate C is here. We have the boundary between plates. This is plate A, this is plate B, this is plate C. So this is my subduction zone or trench, the position of the trench. So this is 4 centimeters per year, and this is 2 centimeters per year. Right? So when I write it on one side, it obviously means it's the same on the other as well. So this is what we're trying to work out. What is the relative velocity of C with respect to B? Now, if I try to work out what the relative velocity of C with respect to B is, so we just have to write it in this particular form. So this is C with respect to B. We can write it as the relative velocity of A with respect to B, right, the standard way, plus the relative velocity of C with respect to A. Once again, see how I've written it, C and B here. So C is here, B is here. So the A comes in the two parts in between. So A is the moving plate in the case of the first vector that we write. It's the fixed plate with respect to the second vector. Now, if we now try to just see what this would mean, right? So what we try to find out is now the relative velocity of A with respect to B. So how do we start? We assume a fixed point. This fixed point, this diagrammatically, this fixed point represents, okay, once again, let me use red here. So let's say this point here, so this is my fixed point. Let's say this point represents the position of B in my relative velocity diagram. So this is my fixed point B. With respect to B, in which direction does A appear to move? Now, as I said, to an observer on plate B, right, if a person is when you're on this side, on the left hand side of the vector, it means that the observer is on plate B and they are trying to observe what is happening on the moving plate, which is the other one. Now in this case, plate A appears to move southwards with respect to plate B at the rate of 4 centimeters per year. So to an observer on plate B, plate A would appear to be moving southwards at the rate of 4 centimeters per year. So what I've just done is to take this vector and just make a parallel line equal in magnitude to this, right, out here with an arrow that is pointing outwards, downwards. So the head of the arrow would be the position of plate A and the tail of the arrow would be the position of the observer on plate B. Now to this we need to add the relative velocity of plate C with respect to plate A. Now for this vector, the observer has to be on plate A. So if the observer is on plate A, what will that person observe, right? If the observer is on plate A, what will that person observe? How will that person observe plate C to be moving? Now, if an observer is on plate A, with respect to an observer on plate A, plate B appears to be moving downwards, right, southwards at the rate of 2 centimeters per year. So if plate A is here, so sorry about this. So we have to move downwards at the rate of 2 centimeters per year. So this is 4, this is 2. So this position is A, this position must be C. So now this is moving downwards at the rate of 2 centimeters per year. So it's exactly on the same line because the vectors are all parallel. So in other words, if I now have to represent the relative velocity between plates B and C, it seems then that the relative velocity of C with respect to B would be a line which is 6 centimeters long. And this 6 centimeters long, to an observer on plate B, plate C will appear to be moving southwards at the rate of 6 centimeters per year. Now, if this is the case, the observer on plate C is observing plate, observer on plate B is observing C to be moving at the rate of 6 centimeters per year, then we have to now place this on this particular diagram. So what do we do? So the one on which the arrow head is, this vector must directly be transported or transported to that particular plate boundary, that particular side of the plate boundary. So if C is the arrowhead, this vector will be the vector that is relevant to plate C. So we draw it out here. So plate C, right, this would be a line of length 6 centimeters here, and there would be an equal and opposite line with the length of 6 centimeters on that side. As you can see now, this vector itself is also once again parallel to the plate boundary between B and C. So since the plate boundary between A and C is collinear with the plate boundary between plates B and C, therefore the boundary between plates B and C will also be a transform fault, right? Which is, however, the velocity associated with it is different. It would be the relative velocity of C with respect to B would therefore be equal to 6 centimeters per year. Right? So you'd have a value of 6 centimeters per year. So work this out and write it properly, and you get that to be 6 centimeters per year here. So this is 6 centimeters per year. So now we know that this is a Dijkstra transform fault. So we have derived the nature of the plate boundary between B and C. Now, once again, I'm cautioning you, how we transport this onto this boundary is vital, because the arrowhead, remember, the arrowhead has to be taken on and placed on the plate which is actually moving. So in this case, B is my stationary plate, C is the moving plate. So this vector that we've derived must be placed onto the moving plate. So the arrow would point downwards on plate C. If you mistake it, you just get an incorrect answer. It would appear to be a sinistral transform fault if you by mistake place this on the other side. Now, let's just get back to the other question now. Let's say I'm an observer here. Now, to an observer here, what would he or she observe with time? So let's say the observer is looking out, right, onto this side. So looking at plate A. So they're actually trying to see what is happening on plate A. So a person on plate A would appear to be moving northwards at the rate of 2 centimeters per year, right? That is what we would see, because the relative velocity vector between plates C and A is equal to 2 centimeters per year. And with respect to an observer on plate C, plate A is moving northwards at 2 centimeters per year. But how would this geometry change with time? So this now means that we have to understand how the boundary between plates A and B, this particular boundary, how is this moving to the observer? Now, you see, to an observer on plate C, so plate C is fixed if the observer is on plate C. To them, a person on plate A would be moving northwards at 2 centimeters per year. To the same observer, a person who is on plate B, let us say anywhere on plate B, will be appearing to move northwards at the rate of 6 centimeters per year. So even though the person is here and the relative, the way these people are moving, right, it's not actually changing the distance between them, but nevertheless, the person here is actually going to observe the distance, the velocities at which the two people will be moving on these two plates would actually be different. So the person here would be moving northwards at 6 centimeters. The person here would actually be moving northwards at 2 centimeters per year. Now, how would this situation change with time? So every year, right, something is happening. What happens to the position of the AB boundary? Will the observer the next year observe the AB boundary at exactly the same position, or will the position of the AB boundary change with time? So for this, it is necessary for us to know how the position of a plate, what is the relative velocity of a plate boundary then? We've talked about the relative velocity of plates, but what we need to understand also is the relative velocity of the plate boundary. So if I'm trying to understand the relative velocity of the plate boundary, in this case, we need to think of how the boundary should be moving. Now, as we know that the boundary is between A and B, so if A and B both move, the boundary has to move in some way or the other. It cannot remain at the same point here, given these velocity configurations. But how will it move? Now, let's just think of what we conventionally accept. what happens is that, you see, if you have any line of particles, let us say, imagine a line of particles on plate A, which is parallel to the trench. Every year, this line of particles will be moving southwards, right? It will be moving southwards. Every particle here will be moving southwards at the rate of 2 centimeters per year. And ultimately, it will be consumed below plate B. On the other hand, if we consider the line of particles at the frontal edge of plate B, right? The leading edge, we call it, the leading edge of plate B, leading edge of plate B. Particles at the leading edge of plate B, they will be moving northwards, right? They will also be moving northwards with respect to the observer at 6 centimeters per year. But this line of particles is actually staying where it is. Unlike the set of particles on plate A, which will ultimately be subducted below plate B, that is, this line, the position of this line of particles with respect to the boundary is changing with time. Every year, this line of particles is coming 2 centimeters closer, and ultimately it will be consumed below the boundary. On the other hand, if we take a line of particles on the leading edge of plate B, that is the overriding plate, then in this case, this line of particles, the position of this line of particles will not change, and therefore all the time the particles that are defining the leading edge of plate B will remain as the frontal edge of plate B. In other words, the trench the position of the trench, or the position of the convergence zone, will always be fixed by the position of the line of particles at the leading edge of plate B. Therefore, what we assume is that the relative velocity of a trench, like boundary, that is the boundary between plates A and B, this will be attached, this is imagined to be attached to the overriding plate. That is, the trench, we assume that the trench is attached to the overriding plate. So the trench is attached to the overriding plate. So this is a very important thing that we need to understand. In other words, the relative velocity of the boundary between A and B with respect to an observer on plate C is the same as the velocity of plate B. That is, to an observer here, the plate boundary will also appear to be moving northwards at the rate of 6 centimeters per year, which is the relative velocity of B with respect to C. So therefore now we've answered our second question. So if an observer is here, with time, he or she will see every year the boundary between A and B moving northwards at the rate of 6 centimeters per year. So at some future point in time, the observer on plate C will see that the boundary between A and B has moved there with respect to the person who is observing, and now looking across the plate boundary, the observer is going to see plate B and not plate A. So therefore, with time, the whole plate configuration for the observer on plate C has changed, and this is without any major movement. It's just a consequence of the automatic movement that is going on between the plates. So we can see that in such a case, right, we would get situations where variations take place in spite of the fact that no major changes or no major adjustments in plate motions have to be taken place. No major changes in the forces concerned. It's just a natural consequence of plate motion. So that's one of the very interesting things we can observe of how geometry changes because of plate motion. Now let's just go into a case which is a little different now then. We've talked so far about we've talked about orthogonal collinear boundaries. So what if we have a case where we have a non-orthogonal collinear boundary? So once again, let's imagine a three-plate system like this, right? And in this case now, let us say that there is a boundary like this, right? And there is a boundary here. Now let's actually once again define three plates. So we'll call this plate A, plate B, and let this be plate C. Now you can see that we've got non-orthogonal relationship between the AB boundary, right, which is north-south here, And we've got the boundary between A and C, which is essentially northwest, oriented northwest, southeast, and is collinear, right, with the boundary between B and C. So this is the same boundary. It's the same orientation of the boundary. It's not the same boundary. The boundary between them is different. So let's just now assume that here also we'll need not put in exact values. We'll just think of, just cases like this. Let's say it's spreading at a particular rate, right? So this is the relative velocity between plates B, the half spreading rates between B and A. Let us also imagine, right? Let's also think, right, that the boundary between B and C, let us just assume that it is actually a convergence zone. And let's, for simplicity's sake, let us assume that this convergence is orthogonal to this boundary here. So now what we would like to find out in this case is what is the nature of the AC boundary. Now, just before this, now let me just once again tell you, just for simplicity's sake, I am giving you the polarity. Let us say that in this case, plate B subducts below plate C. So if plate B subducts below plate C, it means that plate B is the subducting plate and plate C is the overriding plate. So this is the sort of situation we are thinking of now. We can therefore now frame this in the form of two questions. What is the nature of the boundary between A and C, which is this one here? And how does the AB boundary, right, the boundary between A and B, this is mid-oceanic ridge, how does it appear to move to an observer who might be located somewhere here, let us say, right? So if an observer is here, how would he or she observe this boundary between A and B to move, right, with respect to an observer in plate C? So these are two questions that we can answer. So let's once again go into trying to answer these questions. So when we are looking at this, then we can once again just draw this on this side, right? So we have, this is my situation here, so just draw it like this. So we have the boundary here. So this is spreading orthogonally on either side, equal in magnitude. This is my subduction zone. We have orthogonal subduction or convergence in this case, right? This is my plate B, this is plate A, this is plate C, and this is what we're trying to find out. So now, in this case now, the relative velocity, what we are supposed to find out is the relative velocity between plate C and A, right? So this is what we are supposed to find out. How do we write it? Now, by now you should be knowing how to do it. So we write A here, make A the fixed plate, right? B the moving plate in the first part, and the second one that we add onto it, B is the fixed plate, C moves with respect to B. This should be the thing that will give us the answer. So let's just grammatically try to find out what this would be. Now the relative velocity of B with respect to A. So my fixed plate here would actually be plate A. So this is the position of plate A. Now with respect to an observer on plate A, that is a person who is situated here, what would he or she observe plate B to be moving? They would observe it to be moving at twice the relative velocity to the east, twice the half spreading rate here. So this would be this would be twice this length out here. So this position would be the position of plate B in the relative velocity diagram, and this is the position, fixed plate is the position of plate A. Now this is the position of plate B here to us. Now what about the relative velocity of C with respect to B? Now this is the point fixed observer. Now observer is on point B. What would the observer on point B observe? How would they observe plate C to be moving? And to the observer on plate C, then this would be moving in this direction. So if I now move it like this, it would be this way. So this would appear to be the position of C. So this represents the relative velocity of B with respect to A. This represents the relative velocity of C with respect to B, which means that the relative velocity of A with respect to C would turn out to be like this, of C with respect to A. So the arrow would be on this side. So C would appear to be moving southeastwards with respect to A. Now, to find out the nature of the AC boundary, what do we need to do? We need to take this vector, right, and then put it onto this diagram, onto the main diagram. But the question now is, do I put this vector onto plate C or onto plate A? What was the rule? I told you the rule is that you put it on the boundary, right, of the moving plate. So this arrow should be transported onto the moving plate, right? Onto the moving plate on that side of the boundary. So take this, it should have to move it to plate C. So you would see this moving to plate C this way, right? And obviously that means that plate A, right, would be moving this way with respect to plate C. So plate C appears to be moving southwestwards, southeastwards with respect to plate A. Plate A appears to be moving northwards with respect to plate C. What is more interesting is that the orientation of the relative velocity boundary here is such, right, that it is parallel to this particular segment of the plate boundary between A and C, and therefore the nature of the AC boundary has to be a transform fault. So it's a transform fault, and not just the fact that it's a transform fault, it is also a dextral transform fault, because this is right-handed in nature. Now, the question of course comes that if an observer is now placed on plate A, what would the person observe, right, to be the velocity of the boundary, of the ridge between the two plates? How does the ridge move? Now, in this case, right, one of the things to remember is the ridge itself, you can now imagine the ridge to be, the ridge is a line which is midway between here. So, to an observer on plate A, right, plate B appears to be moving to this side with this particular velocity. But what about the ridge itself? The ridge itself obviously would be moving only at half that velocity, right? Would be moving at half that velocity, because half of it is actually spreading this way as well. So the person is only moving is only observing the half the velocity associated with the ridge. So it would be half of this particular velocity. So in other words, right, so the whole system would be such that there would be just a small reduction in the position of this point, and later on the observer would actually observe the position of this particular junction here changing with time. Now, I will not answer this question in this particular class, because I'll be going on to the very next lecture which will deal with the motion of this kind of boundaries. And here we will try to work out what the nature of the motion, right, would be of this particular junction. Now, this junction is a junction between three plates. And in the next lecture, we'll talk about how the junction between three plates evolves in a mobile three-plate system on a flat earth. So we will talk about triple junctions. For this class then, so let's just think of the conclusions that we can draw from this particular lecture. If you have a system of three plates, the boundary between any of these two plates also appears to move to the observer who is located on the third plate in the system. So the observer is on the third plate, so that is essentially being considered stationary, right? So the boundary between the plates may also appear to move. Now the motion of the plate boundary, it may differ from the motion of the two plates. So it may not be the same as the motion of either plate as seen by the observer on the third plate. So if there is a convergent boundary or a trench, these are assumed to be attached to the overriding plate. So the position of the trench is fixed by the leading edge of the overriding plate. That is a very vital and important part, right, of what we have understood now. If you're an observer on a third plate, a divergent boundary or ridge between two plates, that will move with a velocity which is half the relative velocity of the two plates that are separated by the ridge. So we will talk more about this, right, the implications of this will become clearer as we go into the next couple of classes. We will then deal, right, with how the motion of triple junctions, as we call them, right, would actually affect the motions. The implications can be so important to the evolution of the three-plate system. So see you again next time. So we still follow Fowler's book. Keep at it. And thank you very much.